I want to begin, and I'm going to do this a little different than fifth period, I think. When we first started talking about doing work and storing that work as potential energy, one of the things that I think we came to understand was that there was something about the height of an object that seemed to matter when it came to how much potential energy something had. That's an oversimplification. And it's an oversimplification that was created because we started using this in, I would say, arguably simple ways to deal with simple examples, like how fast is a roller coaster going when it makes it to the bottom of the track, or how fast is it going if it started here and makes it to some other location. But I think the takeaway has been that if I look at this particular hillside or something, and we take and compare object A and object B, it would be, I think, easy for you guys to tell me which of these two objects has more gravitational potential energy. Would you agree? Now, I have led you down this road a bit, but I want to also recognize that horizontal line, what would you call that horizontal line? The reference level. So, does it change which object has more potential energy if I move the reference level? I don't believe so. It might change how we calculate the amount of potential energy. But one of the things that we did discuss is that when it came to potential energy and our comparisons, it was a relative measure, and that the reference level was something that we could set somewhat arbitrarily. Now, it wasn't arbitrary in that we could set it anywhere. I told you that the best way to set the reference level was to determine what the lowest location the object could potentially make it to. And that if you use that as your reference level, you'd always be safe. This is an interesting choice for a reference level, especially if I want to know something about what happens if the object makes it to, say, here, right? That might be a kind of an obtuse place to choose the reference level if I wanted to know what happens if the object is here. But the truth of the matter is, I could set the reference level to be anywhere. And our relative comparisons of the two objects would still be the same. Now, this is an absolutely ridiculous place to set the reference level, especially if I want to know how fast something is going at the bottom. But I also want to remind you about where gravitational potential energy came from in our conversations. And if you want to go back to our conversations, we need to put the reference level someplace that is useful for that conversation. I'm going to put it here for just a minute. If you don't remember way back, and when we first started talking about gravitational potential energy, we first did that by saying, well, we know there's something about lifting the object that we can use later. That if I lift an object and put it at the top of a hill or the top of a building, I can push the object off at any time in the future that I want, and that object will fall. And when it makes it to the ground, it'll have a certain amount of kinetic energy. That was where that conversation started. And one of the things I emphasized about that is I can put the object up high and leave it there indefinitely. And at the time of my choosing, I could make sure that that object converted its gravitational potential energy into kinetic energy by pushing it off the edge. Right? The idea is that the energy was stored with the object. And then I expanded that idea to say, well, it's not really stored with the object, it's stored within the relationship between the object and the Earth. Right? It doesn't have that potential energy unless there's an interaction with the Earth, a force that's acting on it all the time to bring that object back down. In fact, that's how we defined how much potential energy it had, by saying how much work is done in taking the object from one location and moving it upwards to another. In fact, we would define work as the force required times the change in position. But those are both vectors, and so we talked about the fact that the amount of work done on the object depended upon the direction of that force and the direction of the displacement. So if we wanted to know how much work was done by gravity as we lift the box up, right? Because it's the interaction between the Earth and the object, not the interaction between us and the object. So we want to know how much work was done by gravity. Well, we are moving the box upwards, that's delta x, but the force of gravity is clearly downwards, that's mg. So the work done would have been mg times h, or maybe h minus h naught, if we wanted to, times the cosine of 180 degrees. Right? The angle between the displacement of the object and the direction of the force of gravity, which gave us negative mg h minus h naught. Now, we never wrote gravity as being, or the work done by gravity as being negative, because we didn't use the work done by gravity. We used the change in potential energy. We defined it as minus the work done against a conservative force. That's how we defined it. Again, an equation in your equation sheet, an equation within your equation sheet. The others are results of those. This is how we came to the conclusion that the change in potential energy was mg h minus h naught. And eventually we just wrote that U equals mgh. But this was the formal derivation. We just got sloppy and lazy, and I said we would. So eventually we just get lazy and just write mgh. But this is where it came from. Do you recall that? All right. Let's say we're sitting next to a hole and we have our ball. And by just some freak of mistaken play with the ball falls down to the bottom of the well. Now, from our vantage point, we were at ground level, and now our ball is gone, and we've lost it. If we want to get the ball, we would have to give the ball enough energy to make it back to where we are, correct? The ball is trapped, though. It's down at the bottom of this well. And because it's down there, it's beneath our reference level. Right? It's below where we are. Now, if I want to get the ball out, just to get it to the surface, it'd be the best way would be to give it some kind of velocity, just to get it up to where I am, where I could catch it. Right? Unfortunately, the only way to do that is probably for me to get down there and throw it up to the top. Right? Because that'd be a way, I guess I could climb out with it, but let's say I don't. Let's say I get down to the bottom and I try to give it enough velocity to throw it so I would come back up here. Maybe I have a friend up here who can grab it right when it makes it to the surface. Right? It's beneath where I am. I just want to get it enough energy to make it just to that surface so it can escape the well. You follow this argument? Now, we talked a little bit about this a couple weeks ago, but the idea is that the ball otherwise, without having this energy, is trapped in the bottom of that well. Now, we try to frame a lot of things like this, and part of the reason we do so is because it works conveniently and expertly in the way we deal with energy. This ball is trapped and will require a certain amount of energy to make it to the surface. We can say that the surface is zero energy, and where we are down here is negative energy. And to get to the surface will require gaining a certain amount of energy to get there. We say one of the things that I think you should have learned by now is that electrons are trapped and bound to their atoms. Chemistry, you learn about what it takes to get an electron away from an atom. What do we call the amount of energy required to take an electron and get it away from an atom? Go ahead. It's called the ionization energy. Faith in humanity restored. Ionizations in a negative way. The ionization energy is the negative energy because that's how much energy it would take to liberate the electron from the hydrogen atom. Not to give it any energy afterwards, not to flick it off into space at some speed, but to just pluck it out of the atom. We list ionization energies as negative in the same way that with the atom too. The ionization energies are negative because they represent the energies that are required to remove the electron from the atom. But when you calculate it, it has to do with the fact that this is an attractive force. It brings these things together. So when we talk about, say, wanting to leave the Earth and go to the moon, one of the things that scientists and engineers had to deal with was figure out how much energy it would take to go from the surface of the Earth to the surface of the moon. The common reference level is kind of gone when we consider like the roller coaster question. So we had to come up with another reference level, or at least another point of reference, perhaps not a reference level, something that would be a common point of comparison between the Earth and the moon. You guys recall what that common reference point was? Where is it? Go ahead. Infinitely far away. We want to talk about taking an object from the Earth and moving it to a point far enough away where it experiences no gravity from the Earth. This can be a common reference level then. That reference level would also be true for the moon and the sun and Jupiter and any of these places. That provides us with our common reference point, also called the standard reference point. In the course of any problem that's dealing with gravitational potential energy or gravitational forces, the common or standard reference point is considered infinity. They don't tell you that, you can assume it to be true. But they might not say reference point, or common reference point, or infinity. They might say the standard reference. And if they do, they are telling you that the standard reference is at infinity, a point infinitely far away. So we talked about the result of this, but today what I'd like to do is talk about the reality of it. Where did that distinction come from? Where did that formula come from? And to do so, I'd like to consider us dealing with perhaps two places near the surface of the Earth. A place that is, say, our initial and our final away from the center of the Earth. Now, before I do this, I do need to make is by writing our force as a vector with this negative sign out front, what we're saying is that the force is always an attractive force. That if we connect a line from object 1 towards object 2, the force on object 2 will be towards object 1. Now, I want you to think about this a little bit. You guys learned that electrons are negative and protons are positive, right? You also learned that opposites attract. So if you multiply negative times a positive, you get negative. The force between the electron and the proton looks very much like gravity. This is the force between an electron and a proton, except it doesn't have this implied negative sign. If Q1 is positive and Q2 is negative, it makes the whole thing negative. It's an attractive force. If Q1 is positive, Q2 is positive, makes the whole thing positive. It's a repulsive force. If Q1 is negative, Q2 is negative, the whole thing's positive. It's a repulsive force. This is a way you can say opposites attract and like charges repel. So electrostatics follows a similar inverse square rule, as does gravity. It just does so for a different intrinsic property, charge. So we'll find a lot of the same things related to energy exist inside our electrostatic problems and inside the atom, just as they do inside gravity. We don't need that any longer. Let's talk about this. Now, I want to apply all the same rules we did just a few minutes ago when it came to finding out the change in potential energy and going from R1 to R2. Okay? The difference is that this force isn't constant, right? This force changes between Ri and Rf. So I can't use force times displacement to calculate work. Do you remember what we're going to have to do instead? Work is actually defined as the integral of F dot dr. All right, we ready to go? I'm going to start by recognizing that we're going to move the object from Ri to Rf. And I want to throw down something that I didn't say earlier that probably needs to be said. It was said first semester, but it's been a while. The dot product here actually just tells us that this change, this displacement, will be path independent, meaning it doesn't really matter whether I travel directly from here to here or I travel, some obtuse path. The change in potential energy is the same. It's a path independent calculation. The only part of the work that matters is the part of the force that's towards the center of the planet. So when we talk about how much work is done, I don't need to worry about the path, but I also have to worry about the dot product. I'm going to put my integral as Ri to Rf, starting at one place and ending at the other. And I'm going to sub in my expression for force like so. This will be the work done. Now, this is not a particularly hard integration to do, but I did just grade your tests, so I think I need to be explicit here. So I'm going to go through each of the variables here, and I'm going to ask myself which of these variables has anything to do with R and which ones don't. So does M1 change as I go from Ri to Rf? Does M2 change as I go from Ri to Rf? Does G change as I go from Ri to Rf? No. Remember, G is the universal gravitational constant. In fact, we think, and there's been a lot of evidence to support this, that it is the same everywhere in the universe. We've based our standard model of how gravity works on that idea. So G is the same whether we're here or at the moon or at, I don't know, some other universe. Well, maybe not some other universe, but some other galaxy for sure. Does R change as I go from Ri to Rf? Yeah. In fact, that's the reason why we can't use just F times delta X, because the R is changing and therefore the force is changing. With that, I can pull out the negative sign M1, M2, and G and be left with the integral from Ri to Rf of 1 over R squared dr. And that would be the work done. We all okay with that? One over R squared can be written as R to the negative 2. Is that hurting anybody's feelings there? You might want an extra step in there if you didn't remember to do that and don't want to be confused when you review your notes later. That's just a polynomial, though, and not a particularly special one. So I think we can find the antiderivative by using our polynomial rules. So I want to go through the polynomial rule because it was gotten wrong by more than one of you. So if I recall, the antiderivative of the polynomial is to add 1 to the exponent and then divide by the new exponent. I'm saying all those things because I had people do some weird stuff. So I'm going to add 1 to negative 2. That gives me negative 1. Then I'm going to divide by the new exponent. That's negative 1. And I want to evaluate this from Ri to Rf. All good? Okay. I guess the next step would be to put in the limits of my integration. So I'll have negative 1 over Rf minus negative 1 over Ri. That all okay? I'm going to go ahead and distribute. Is that okay with you guys? The negative M1, M2G and all that? How are we doing? All good? Well, I didn't want the work. I wanted the change in potential energy. So I'm going to write this as delta U, but we know that is minus W. So won't that be minus M1, M2G over RF minus M1, M2G over Ri? Now, hear me out. You might want to write another line. I'm not going to. Right, it's delta U, the change in potential energy. So that suggests that this is U final and this is U initial. That okay? Our standard reference level is when Ri is at infinity. So if I want to pick a point of comparison for the Earth and Moon, I want to take this value and put it at infinity so I know how much potential energy I have when I'm on the Earth. If I use that same reference point for the Moon, I can then compare the Earth with the Moon, or the Earth with the Sun, or the Earth with Jupiter, or the Earth with Mars, right? That suggests that when I goes to infinity, what happens to this term? It goes to 0, right? If Ri becomes very big, that's infinity. That whole term gets very small. So for those who don't understand the whole idea of limits, the limit as R goes to infinity is to make this term non-existent. Which gives us not delta U, but just U. Gravitational potential energy as an absolute measure is merely rated based on where you are relative to an infinitely far away place. These measurements are made relative to wherever you happen to be in the universe. So if I'm at a location, say, bless you, the surface of the Earth, then I would measure this as R, the radius of the Earth, because I'm measuring it relative to a point infinitely far away where I brought an object from infinity and sat it on the surface of the Earth. You follow what I'm saying? If not, let's just make a quick idea about that. The whole point here is that my potential energy here compared with the standard reference point is by comparing a point so far away it's at infinity, as if I was brought from infinity and deposited here. Now, I wasn't brought from infinity and deposited here. It's like that movable reference level that we talked about at the very beginning of class. We're using infinity as the standard reference level for all things to be measured. I wasn't actually brought from infinity to here. I want to make sure you understand that. We're using it as a point of reference. But by using that as our point of reference, I would say that my energy, my gravitational potential energy for Shelton, is going to be the mass of Shelton times the mass of the Earth times g over the radius of the Earth, but it is negative. That my energy is negative because I am trapped on the Earth. I am in a gravitational potential well. The only way to escape it is to add energy to me. If I could give myself enough energy, I could get back to a place infinitely far away. So all gravitational potential energies, when dealing with planetary motion or satellite motion or anything where the force isn't constant, chooses a reference point at infinity, but makes the energies negative for these comparisons. That means anything that's in orbit has negative energy, negative total energy. They have to. If they didn't have negative total energy, they would have enough kinetic energy to escape. So consider an object that is in orbit. Nope. That's not what I want to consider. Say Mr. Shelton is in orbit. I'm going to have some velocity, which means my total energy is going to be the potential energy I have plus the kinetic energy I have. That would have to be my total energy. Now you guys already know, because we've done this before, that you can figure out your kinetic energy because we know that there are some relationships between the force of gravity and the centripetal acceleration that require how fast I have to be traveling in order to be traveling in an orbit around the Earth, right? We've done that already. You can figure out that speed. Right? Remember that from first semester? Things like net force equals MAC, and then net force equals mv squared over r. And from there, we can start building a profile of how much energy it would take to be here. It would not be hard to do, and we're going to do that. But no matter what, this number is a negative, this number is a positive. But if I'm in orbit, I didn't escape the Earth's gravity. I'm still trapped here. That number total is going to be negative. If I was traveling fast enough, I'd have enough kinetic energy to not be trapped there. We did that the other day, remember? Let's say that instead we put Mr. Shelton into a cannon, like that kid in the hall would like to have done. Put me into a cannon. Shoot me far away. The only way you could get me out of the Earth is to bring my total energy to zero. Now, we talked about this a little bit already, but let's review it for just a minute. If I wanted to send Mr. Shelton away, well, I have to start with the fact that if I'm on the surface of the Earth, this is the amount of negative energy I have. This is the gravity well I'm trapped in. And I'm going to add kinetic energy to me to get me out of the Earth. To do so, I need to bring my energy to zero. This would get me to a point where I would no longer have any velocity, but I would no longer fall back towards the Earth, because I'm infinitely far away and the Earth's force no longer can contain me. Now, this point doesn't really exist. You can't be infinitely far away. There's no place in space where the Earth can't be pulling on you a little bit. But remember, it really doesn't matter, because just because you get away from the Earth doesn't mean you get away from the mass of the universe. There's always going to be something out there. So this is a bit of a thought experiment, as if the Earth is the only thing in the universe. Okay? But we don't ever really have anything escape. Now, we can do some quick work here, can't we? Just do algebra. We already did this algebra once, so I don't feel like doing a lot of work for the algebra a second time. Cancel out the MS's, solve for the velocity, and we get the square root of 2meg over RE. This is the escape velocity to escape the Earth. And there's important details here, like it doesn't really matter what it is that you want to escape the Earth's gravity. They all have to have the same escape velocity. You know, the mass of the object actually canceled out. That doesn't mean they all have to require the same energy. Bigger objects will require more energy than smaller objects, because energy requires knowing how much mass there is. What we're saying here is that the escape velocity is the same for all of them. No matter what it is you want to leave the Earth, this is how fast it has to be going to leave the Earth. Does that make sense? Now, the escape velocity is a neat concept, but just like I said, it's just a concept. We don't actually need to get to the escape velocity of the Earth. That would be great. We'll just fall into the sun then, or whatever we happen to be closest to. One of the realities of space travel is that if you wanted to go from one place to another, you don't have to escape and get to the escape velocity. The truth is, you just need to get to a point where the force from the other object is going to be greater on you than the force of your origin object. So if I want to get to the moon, well, I just need to know how much energy it takes to get to the point between the Earth and the moon where the net force is 0 and have just enough energy to pass through that point. I definitely don't want to stop there, right? If I stop there, I'm trapped. Except in reality, both of those things are moving, probably more complicated than that. But if I can make it to that point with just a little bit of speed and pass through it, well, then the moon's gravity will do the rest. It'll pull me towards it. In fact, the truth is, if you want to know how much energy it takes to go to the moon and back, the minimum amount is the amount to get to this point from the Earth, and then the amount to get to that point from the moon, right? Because once you land on the moon, you want to get back there. If you want to get, or if you're just, Apollo 10, you want to orbit the moon, well, then you don't need as much energy to get back to this point, to get back to the Earth. Now, you'll probably need extra fuel, things like maneuvering, and you don't want to crash into the moon. You'd probably like a soft landing. There's probably other factors involved in determining all the energy requirements. This just represents the very minimum. So if you don't want to crash into the moon and you don't want to, say, send your astronauts off the Earth so fast that they burst into flames due to the friction on the surface of their ship, you probably have to make other allowances for how you use this energy. You may have to use some of it just to kind of be careful that you don't kill your occupants and stuff like that. But just to tell you just the minimum. And we would still compare it to, say, a point infinitely far away. How are we doing? We doing okay? Any problem with this? Now, I know we're going to be short on time, but the look on the face of some of you suggests I need to remind you about something. Can you take a moment and just put together what the centripetal relationship would look like for something that is in orbit, say an orbital distance r away from the center of the Earth? Do you remember how to do this? Set up an orbital relationship. Tell you what, I'll help. I'll remind you that to be in a circular orbit, net force has to equal MAC. If the only force we're talking about is the force of gravity, which we know to be opposite direction of r, well, that's going to be mass of satellite, mass of Earth, g over r squared. This is not the radius of the Earth. This is the radius of the orbit, right? We're not at the surface of the Earth anymore. We're orbiting the Earth. So I'm just going to use a lowercase r here. This has to equal m, well, remember, we're talking about centripetal acceleration. We're traveling in a circle. So that would be your orbital speed squared divided by the very same r, because you're traveling in a circular path, and this r represents a circular orbit. Now, I'm going to notice something. This m is the mass of the satellite, right? I'm also going to notice I can cancel out the r's. You notice that too? Well, that means ms MEG over R equals MS VS squared. Do you guys see that? One more little tiny thing. If I just put a 1/2 in front of it, do you realize that's the kinetic energy? I just multiplied both sides by 1/2. That means this has to be the kinetic energy of an object in orbit. Now, you may not see where I'm going, but do you notice that this looks a lot like the potential energy too? We'll pick up here tomorrow.